In this video, we're going to be looking at transformations of graphs and functions. So you're going to need your graphing calculator because we're going to do this sort of as a discovery type lesson. So let's start with example 1. It says use your graphing calculator to first graph f of x equals x squared. So we go into y equals, we're going to put in f of x equals x squared. Hit enter, and then it says to graph g of x equals x squared plus 3. So we're going to put in, again, the second y2, that's going to be our g of x, equals x squared. Make sure you're out of exponent land, and then plus 3. Make sure that plus 3 isn't up there with the exponent. Now we may have to set the window because we were using our graphing calculator for some other things. So looking at this sketch here, it's going to tell me how to set my window. So I'm going to go in window before I show my graphs, and I'm going to set my x from -3 to 3, which it already is. We're going to set our y from 0 to positive 1, 2, 3, 4, 5, 6, 7, 8. So our y max is 8. Now hit graph. There is our f of x equals x squared, and there is our second graph. So using two colors here, I'm going to do the first graph. It looked something like this. I'm just sketching mine. I'm not actually checking to see if the points are correct. I'm just getting a general idea. And that was f of x equals x squared. What happened when we then graphed f of our g of x equals x squared plus 3, you note 1, 2, 3, the graph moved up on my y 3 counts, or 3 tick marks on the graph. Now I did my narrower there, and I didn't mean to do that, but again, I'm just doing a general sketch. So how are the two graphs alike? They have the same shape. How are they different? The way that they're different is g of x was moved up, or vertically up, 3. It was moved up 3. We call that a vertical shift. All right? Let's go back to our graphing calculator, and in example 2, once again, we're going to keep f of x equals x squared. So when we go, let me move it over so we can see. When we go in, we're going to keep the first one, but we're going to take out the second one, or change it if you would prefer. We're going to change it to take away 4. So g of x is x squared, take away 4. Now we're going to change our window, as you can see from our picture here, that x's are going to be negative 1, 2, 3, 4. So 1, 2, 3, 4 to 4. So let's go into window, -4 to 4. And then our y's are negative 1, 2, 3, 4, 5. So we're going to go -5 to positive 5. And let's look at that graph again, knowing that the first one is the same thing we got above. So my first one is shaped basically like this. But when I went to graph g of x is x squared minus 4, 1, 2, 3, 4, it moved my graph down 4. So it says, how are the two graphs alike? Again, they are the same shape, but how are they different? G of x was moved down 4. So that was, again, a vertical shift, but it was a shift down. So our conclusions about vertical shifts are that when you start with a function, and I will word this more succinctly in just a minute, when you start with the function, for example, x squared, and you add on to the end, so adding on to the end, and that is important that it's the end of a function. What does that do? It shifts the graph up. And subtracting from the end of a function shifts the graph down. And we call both of those a vertical shift. And this is the one that is fairly intuitive. Adding on or subtracting from the end is going to move the graph up or down. All right, let's look at a second one. So in example 3, we're going to go back in our graphing calculator and we are going to go to our y equals. Once again, we're going to keep that x squared. So come down, and this time I want you to hit clear, because what we're going to enter this time is parentheses x minus 2 quantity squared. So it's parentheses x, my x didn't come up, minus 2, close the parentheses, and now we're going to square that entire thing. So we are not adding on to the end or subtracting from the end. Instead, we're doing it within the function before it was squared, before the function operator was used. For our window, let's use negative 1, 2, 3, 4 and positive 4, and then we're going to use negative 1 to 1, 2, 3, 4, 5. So let's put that window in. Negative 4 to positive 4, negative 1 to 5 for our y. Hit graph. There, once again, is the first function that we continue to get, but look what happened to the second one, the g of x. So here is my first one again, just a general sketch. I'm not plotting individual points. I know it's not totally accurate. I'm okay with that. My function was x minus 2, and look what happened to the base of my function. It went to the right 2. It went over to here, which might be counterintuitive, and I made mine kind of crooked, but that's all right. You might have thought, oh, I'm subtracting, so it's going to go left, but it didn't. So how are the two graphs alike? Once again, they are the same shape, but subtracting inside of the function made my graph, let me move my calculator, it moved to the right 2, and that is called a horizontal shift. And the horizontal shift occurs inside the function, not at the end like our other one did. So you see the difference? All right, let's try another one, but this time we're going to add 4. So going back to our y equals, we're going to keep our first. I can just scroll over, and where there's a minus, I'm going to type right over it. Where there's a 2, I'm going to put a 4. Now notice, I'm adding 4, but I'm still inside of the function. Now use your common sense. If subtracting 2 moved it to the right, what do you think adding 4 is going to do? And we're going to have to, by the way, change our window. So in our window, my x min is negative 1, 2, 3, 4, 5, 6. So negative 6 to positive 2, we're going to keep our y the same. Let's hit graph. There's our original again. We know that that's going to be the same because that's the parent function. But if your intuition told you that if a minus 2 moved it right, a plus 4 is going to move it left, you were correct. We went over 1, 2, 3, 4, and the vertex, it's called, of that graph is sitting right there now instead of at the 0, 0. So how are the graphs alike? Once again, they are the same shape. How are they different? The graph moved 4 left. Again, it was a horizontal shift. So adding a 4, let's put adding, but it was inside the function, not on the end. Inside the function moves the graph left. So it's a little bit counterintuitive. Adding moves it left. Subtracting inside the function moves the graph right. Counterintuitive. All right, let's continue in this manner, going to our next page, and we're now going to use a combined transformation. So let's first take a look at our equation and see if we can figure it out. It says graph the function f of x equals x plus 3 squared minus 5 without using the graphing calculator. Start with the parent function. So I know that the parent function, that's what we call it, is this function stripped down to this, just the very beginning of it. So that would be f of x equals x squared. Well, we know what that looks like. That looks like that. We've graphed it now several times. So let's look at what was done to that function in this combined. First, inside the function, I have a plus 3. What did we just learn that horizontal shift is going to do? By adding 3, it's going to move it left 3. And then we want to do this one last. On the end, when you subtract 5, that's a vertical shift. It's going to take it down 5. So let's look at that, and then I'll do it in green. So first off, this graph is going to go left 1, 2, 3. So that would go like this, but I'm not going to draw that yet. And then it's going to go down 1, 2, 3, 4, 5. So it's now going to be sitting right there, and it would look something like this. So that was 1, 2, 3, down 3, or left 3, excuse me, and then down 1, 2, 3, 4, 5. Let's see if we were right. Go into y equals, leave your first one the same, just scroll over, and we're going to put plus 3, and then keep scrolling over, and now put take away 5. Hit enter. Now go into window, and let's change this to negative 5, 5 for our x, and let's do our y as negative 6, 6. All right, hit graph, and let's see if we were right. There's the parent, and then over 3 and down 5. That's exactly what happened. Left 3 and then down 5. So you can actually, without even looking at the points, we can see what's happening. I didn't even have to do an XY table. I could have done an XY table, but I really didn't need to, as long as I understand what is happening to that parent function. Okay, those were horizontal and vertical shifts. Remembering that, let me bring this down again. The horizontal shift happens inside the function before it's squared or whatever's being done to it. The vertical shift happens on the end. Let's look at what is called compressions and stretches. So we're going to start again using our graphing calculator. We're first going to graph f of x equals absolute value of x. So go into y equals, go ahead and hit clear for both of those. Go back up to y1, and we're going to do absolute value. That's in the catalog. So second catalog, it's the first one. Hit enter of x. Hit enter. And now we want to do 2 times the absolute value of x. So we're going to multiply it by 2. So I'm going to go 2 second catalog absolute value of x. Hit enter. Let's adjust our window. 1, 2, 3, 4, 5. Actually, I think our window from the last one is probably okay. So let's go ahead and hit graph. We know that the absolute value function looks like that. Look what happened, though, when I multiplied it by 2. My second one is this narrower graph. So my first one, again, I'm not being accurate with points. I'm just sketching a general shape. My first one looked like that, but my g of x, when I multiplied it by 2, it narrowed it, and I exaggerated a little bit there. And so how are those two graphs alike? They're basically the same kind of shape, but one is narrower. So it's a narrower second graph. I'm going to put narrower second one. Narrowing the one is called a vertical stretch. So what's happening, it's like you're taking that original graph and you're grabbing those 2 points and you're pulling up. If you stood up and you reached your hands over your head and you pulled up, it would make you feel narrower, skinnier. So when you multiply by 2, you're pulling up those points by double and it's narrowing the graph when you multiply by 2. Now we're going to do it again in example 7, and we're going to multiply by something that is less than 1 but greater than 0. In other words, a fraction. So it's like there's going to be a fraction of the power that's holding up the original graph. So think about what that might look like. So let's go back to our y equals. We're going to keep the first one, but on the second one, I'm going to take out the 2 and I'm going to put in 1/2, but I'm going to do it as a decimal just because it's going to be easier. I'm going to put in 0.5. All right, so it's going to be 0.5. I forgot to do an insert, so I have to do catalog absolute value of x, enter, and I'm going to go ahead and keep my same window. So let's hit graph, and remember the first one is going to be absolute value of x. So let's hit graph. There's our first one that we've been doing. Now look at the second one. It's like, oh, it only has half the energy, half the power, so it kind of falls apart a little bit. So our first one looks like absolute value of x. We know what that looks like. But the second one only had a fraction of the strength to hold it up. That's how I think of it. So again, it's basically the same shape. It's the same basics shape, but it is wider, or it widens that graph. That is called a vertical compression. And let me tell you why it is compressed. It's like I went up here on these points and I compressed them, pushed them down. All right. So that widens it. The key words here are multiplying by something that is greater than 1 narrows it because it's powerful and it's pulling up and making it skinnier. A fraction of it, it doesn't have the strength to stay open. It widens that graph. That's called the compression. The other one is called the stretch. Okay, so conclusions about stretches and compressions. So multiplying a function by a number greater than 1 stretches the graph, which narrows it because it's stretching up, so it narrows. Multiplying the function by a value, I'm going to write the word value, that is less than 1, but it has to be greater than 0. You can't multiply it by 0, obviously. So the value that you're multiplying by means it's a fraction. It compresses the graph, which causes that graph to widen or to get fatter. All right, let's look at another function. We're going to go back to our x squared function because it's an easy one to see. And we're going to talk about reflections across the x-axis and y-axis. So in our graphing calculator, we're first going to graph x squared, and then we're going to write negative x squared. So go into F1, y equals, hit clear for the second one also. The first one, we just want our x squared again. Now be careful on the second one. I want the negative of x squared, the negative of x squared. For our window, let's change our window a little bit. Let's change it to -4, 4, and then for our y, 1, 2, 3, 4, we'll change it to -5, 5. Hit graph. There's the first one. Now watch what happens with the second one. Oh, where did it go? So let's look at the first one. Here is our f of x equals x squared. But when I put that negative in the front, not a subtraction sign. By the way, let's look at our graphing calculator. When I put in the negative, I used this button, not this one. You will get an error. You can't start out a sentence, numeric sentence, with a subtraction sign. Okay, you have to have something to subtract from. So we use the negative sign. When we did that second one with the negative in front, it took that graph and it reflected it across the x-axis. So how are the graphs alike? They are definitely the same shape. How are they different? G of x is, I'm going to say, flipped, reflected, across the x-axis, and that is called a reflection. Flipped across the x-axis. Now, what really changed? Did the x become negative? Think about it. It didn't. It was the y that became negative because the whole thing had the negative in front of it. That represents y. Let's look at our next little discovery that we will do. Go into your y equals, well, I'm fumbling around with pages here. And on this one, we'll use a different function. We're going to use square root of x. So go into y equals, hit clear for both functions, go back up to y1, and let's put in square root of x. Square root is right above the x squared button. Let me bring this up a little bit. So we have y1 equals second x squared square root of x. Hit enter. And now what we want to do is we want to put the negative inside the function. So the x is becoming negative. It didn't go out front. Notice there's a difference between this versus, let me get this down so you can see it, versus the negative being out front. We already know what that's going to do. That's going to take it across the x-axis. But what does it do when the x itself becomes negative? So you're going to go square root of negative, on your graphing calculator right here, negative x. Hit enter. Let's adjust our window to match this. So window, we want our x to be negative 1, 2, 3, 4, 5. So negative 5 to positive 5. We want our y to be negative 1 up to 1, 2, 3, 4, positive 4. Hit graph and watch what happens. There's the square root of x. Oh, look where the negative square root of x is, or the square root of negative x, excuse me. So here was our first, we know that. That's square root of x. But what happened when I made that x negative, it took it across the y-axis. So this is square root of negative x. So again, it's the same shape, but g of x was flipped across the y-axis, which is also called a reflection. Okay, so what are the conclusions? This is really important. When you replace y with negative y, what happens is it reflects across the x-axis. And we actually already knew that because we did that when we did symmetry. Okay, that was example 8. When you replace x with negative x, like we did here inside of the function, that reflects across the y-axis. And again, we already knew that because we did that with symmetry. If you want to look at a summary of graphing techniques, you can look on page 259 of your textbook. But we're going to look right now at doing some combination transformations. So let's look at example 10. It says find the function that's finally graphed after the following 3 transformations are applied to this function. We're not going to use our graphing calculator. We're actually going to do this one step at a time. So it's kind of a summary. So first off, we want to take this function, y equals absolute value of x. We want to shift it left. So that's a horizontal shift. So what that is going to give me is my new function of y equals, remember, horizontal shifts are inside the function, and it's counterintuitive. Left means it's going to be x plus 2 inside. So that would be my new function. And if you don't believe it, check it on your graphing calculator and you will see that using this function, we'll take this one and shift it left 2. You can prove it does. We're not going to take the time. All right, now we want to take this function, same one, and we want to shift it up 3 units. Okay, so up is a vertical shift, and that happens on the end of the function. So I add a 3 to the end of the function. Now I want to take this function and I want to reflect it across the y-axis. Well, going back up here, to get it reflected across the y, I have to put a negative x in for x. So it's going to be y equals, take out the x, put in a negative x, keep the plus 2, and then plus 3. And this is the final function that we have when we do this. Now, this next one is to show you that it matters what order you do things in. So please follow along very, very carefully with this. We're going to do the same 3 things in each example A, B, and C, but we're going to do them in a different order. And you're going to see that you get something different depending on the order that you apply those transformations. So it says, starting with the parent function, write the resulting equation when the following transformations are applied in the order given. So A, write the equation of the function whose graph is the graph of f of x equals x squared, but first we're going to send it 4 units up. So let's just do these in order. Here is the parent. Now we're going to send it, I'm going to use y. We're going to send it 4 units up, so that would be this. Then I'm going to stretch it by a factor of 3. So that's going to be y equals 3x squared plus 4. And finally, I'm going to reflect it across the x. Across the x means the whole thing. And by the way, I just did this incorrectly. This should have had parentheses. Sorry about that. We're vertically stretching what we already have by a factor of 3. So this should be 3x squared plus 12. Now we want to reflect that across the x. So to get it across the x, I have to make the whole thing a negative in front of what I have. So it would be like make it a negative y, to put a negative in front of the whole thing. So it's y equals negative in front of the whole thing. You can leave it like that, or you can distribute that, negative 3x squared minus 12. There is my final function for doing the 3 transformations in that order. Now let's do them again in a different order. Start with y equals x squared. This time we're going to stretch it by a factor of 3 first. So y equals 3. The only thing I have to multiply by is the x squared. Not like up here where I had to do the whole thing by 3. Okay, that was that part. Now we're going to translate it 4 units up. So that's just going to add a 4 to the end. So y equals 3x squared plus 4. And now we're going to reflect across the x. So that means the whole thing has a negative in front, 3x squared plus 4, or y equals negative 3x squared minus 4, because that negative applies to everything on that right-hand side. Finally, we're going to do the same 3 transformations again, but you're going to see we're going to get something different from this and something different from this. So we start with y equals x squared again. This time we're going to reflect that across the x-axis first. So y equals negative x squared. No parentheses. I'm not putting in a negative x. I'm putting in a negative in front of the whole side. That's a negative y. Now I'm going to send that 4 units up. Y equals negative x squared plus 4. And now I'm going to stretch by a factor of 3 the whole right side. So y equals, I've got a 3 times negative x squared plus 4, which gives me negative 3x squared plus 12. Notice, different, different. It really matters which order you do things in. A couple things to remember here. If you're reflecting across the X, the whole right-hand side gets a negative applied. And if you are vertically stretching, the whole right-hand side gets that stretch applied. So I had to use that distributive property. All right, let's look at last one. Number 12, graph the function this time that is f of x equals the square root of 1 minus x and then plus 2. Start with the parent function and graph each transformation till you get to the final function. So we're going to start here with the parent function. We're going to call that p of x. P for parent is square root of x. So I'm going to make a chart down here that shows points. All right, so I'm going to make this big chart, and I'm first going to have p of x. So if I just want to say what points do I have if I plug in numbers for x and then take the square root? Well, I know I have to plug in 0 or positive, so I'm going to have the point 0, square root of 0 is 0. 1 square root of 1 is 1. 4 square root of 4 is 2. So I know I have the point 0, 0, 1, 1, 1, 2, 3, 4, 2, and I know that my shape is about like that. And you can test it in your graphing calculator if you want. Let's go to the second thing that we're going to do. The second thing we're going to do is we want to start inside. Now this is where it's a little bit hard. What we're going to start with inside is, let me rewrite this. This is the same thing as negative x plus 1. I don't want to apply that negative. I just want to add the 1. So my second function, which I'm going to call g of x, is going to be the square root of x plus 1. So here I'm going to have g of x equals square root of x plus 1. Now, let's think about from our original points, what is changing? What is changing? So I'm going to say, if I let x be negative 1, then I would have square root of negative 1 plus 1 is 0, and square root of 0 is 0. If x is 0, I have square root of 0 plus 1. So you can see from here, what is changing is that as I keep my x's, my y is going up by 1. And I was allowed then to drop down to a negative 1 for my x. So if I now put x is 3, square root of 3 plus 1 is square root of 4 is 2, etc., etc. I wanted to keep those whole. I didn't want to have any decimals or fractions or anything. So what was I really doing? I started with a parent function, and because this is inside the function, that means it was a horizontal shift going left 1. So what I did was I subtracted 1 from my x, those points. So I now have the point negative 1, 0, 0, 1, and 1, 2, 3, 2. So now it looks like this. And we know that because when you add something inside, we know that's a horizontal shift left 1. You can prove that in your graphing calculator if you don't believe it. All right, from there, let's go to h of x. Now I want to keep what I had, but this time I'm going to turn that x into a negative x. So I'm getting close to what I had. And what that does, it reflects across, putting a negative x in for x, it reflects across the y-axis. So h of x is equal to square root of negative x plus 1. So whatever my x is, it's going to become the opposite of that. So that gives me the point 1, 0. It gives me 0, 1, because the opposite of 0 is still 0. It gives me negative 3, 2. So what did I do? the x value becomes its opposite. That's what is happening with the points. When I plot those, I have the point 1, 0. I have 0, 1, negative 1, 2, 3, 2. So it reflects it across that y-axis like we said it would, and now it goes that way. That's from here to here. Finally, I don't know what color I have left. We'll use this blue. Finally, we're going to graph our f of x, which is, now this is the same as that. So I can leave it like that, negative x plus 1, 1 minus x, same thing. But now I'm going to add a 2 on the end. Well, we know what that does. That is going to be for our f of x equals square root of negative x plus 1 plus a 2 on the end. That is a vertical shift up 2 from here. So it's going to go up 1, 2, and it's going to go like this. What's happening to the points? I'm going to add 2 to every y because it's my y that's going up. So that's going to be 1, 2, 0, add 2, 3, negative 3, add 2, 4. And if I had graphed it correctly, you can see that. Now you can prove that in your graphing calculator. So that's taking it step by step and doing the graph steps.